We're now going to look at some other geometric figures, and we'll start with polygons. So a polygon is just going to be a figure in a plane that's bounded, which just means that it's all enclosed, and it's closed, which means that all of the sides are going to connect by these straight line segments. So we typically describe a polygon based on the number of sides that it has. So a triangle has 3 sides, and it would look something like that where I close it in. A quadrilateral is the word for a polygon with 4 sides, and they can be any angle. I need to draw. It's hard for me to close these in. A pentagon has 5 sides. And a hexagon has 6 sides. There are certainly more. We have things like an octagon with 8 sides, a decagon with 10 sides. When you start getting into really large polygons, we tend to just call them like 17-gons if you had 17 sides. But we're just going to focus on some of these figures that have between 3 and 6 sides. Now, if we connect 2 non-adjacent vertices, so you're looking at 2 corners that aren't next to each other, we would call that line segment a diagonal. And I can draw one of these in to all of the shapes except the triangle, because in the triangle you do not have a vertice that's not adjacent to one of the other ones. So we can't draw any of these diagonals in triangles, but we can draw a diagonal in every other shape. And there's multiple diagonals that you can draw within these shapes. Some of the properties that we need to know is first that the sum of the interior angles, those are just the inside angles, in a triangle will always be 180 degrees. So if we have a triangle shown here in example 1 and we want to find the measure of the missing angle, we need to add the given angles, 80 plus 55, and that gives us 135 degrees, and then subtract that from 180. That gives us 45 degrees for the missing angle. That tells us that the measure of angle A, and you see here I put a little m in front of angle A, that equals 45 degrees. When you put a little m in front, it just stands for measure. Notice here that I was able just to use the letter A because it was clear exactly what angle was there at the vertex A. There were no other angles drawn. Now in example 2, we have this figure where side AB is parallel to DC. So we have this line and this line parallel, and we want to know the measure of ACB. So we want this little angle right here. So what do we know? Well, we see here that we can actually create a transversal with the side AC, making that 38-degree angle that's given an alternate interior angle with the angle there at vertex A. Knowing that, we now know that there's a 90-degree angle there at B because of the little square, and we just found the 38-degree angle. That adds up to 128 degrees. Angle ACB is going to equal 180 minus the other 2 angles in the triangle, which will give us 52 degrees.